of Chile, which are co-owned and cooperated by ISO, as well as important to remember in the times that
Okay.
we are living
I
in,
think I got the
where
audio
the world
set
is
up.
not
Sorry.
running in
6
one
a.m. Kyle
direction.
is not functioning properly. Had no
ISO was
sound in my
founded 60
stream.
years ago precisely to
But
foster international cooperation
we're here now, I
in
believe.
astronomy, so we can jointly tackle the biggest open questions in the universe. And indeed, the key motivation for ISO to put its telescopes in the southern hemisphere was to enable science to be done around the center of the Milky Way. So this is why it's such a big pleasure today to be here hosting this event. Together with me, I have two of the leading figures of the collaboration, the EHT project director, Hope van Lankevelde, chief scientist at JIVE and also professor at Leiden University, and the founding chair of the EHT board, Anton Zensus, director of the Max Planck Institute for Radio Astronomy in Bonn. Anton will later be telling us about the European facilities involved in the EHT, and now Hope will now present the main result. So over to you. Thank you very much.
Thank you, Javier. When I entered the field of radio astronomy as a student, I was told about this enigma, this mysterious radio source, Sagittarius star, at the heart of our galaxy. I observed it at long wavelengths, and there it appears to be blurred. It's very exciting here today to show you today this best ever image of that enigma, Sagittarius star. I will do that with my team, or with the team, but I would first like to remind you that the team is much bigger than fits in
I want to see it.
In fact, it's bigger than fits
in
auditoria around the world where this press event is taking place simultaneously. We are over 300 people on these papers, and only very few of us get to be staged here today to share the results.
Of course, it's a team effort.
To share the result, we will be flying into the heart of the galaxy, some 27,000 light years away from us. We will do that in 45 seconds. That's a violation
45 seconds?
right away, but maybe
gotta get my camera ready for this.
Only violation of Einstein. So we start out from the plains of...
oh, they got the whole animation here. Let's go.
And we're going to zoom in to Sagittarius.
Oh, this is so hype.
Which is high in the sky above the northern Chile. And we will go and zoom in first in the optical, but we have to switch to the infrared because there we can penetrate all the way into the galaxy.
Right.
We leave tens of millions of stars behind, and we get to the place where stars are in orbit around a dark spot. And when we switch then to our radio eyes and we use a network of telescopes to resolve further and further, I can present to you the image of Sagittarius star.
Oh my gosh! Look at that! Oh my goodness. There it is. Sagittarius A star in all of its radio beauty. Wow. Oh, look at that. Yo, that's sick. Let's compare it to the M87 picture right here.
Team in reverse order here on stage because that went really fast. Christian Fromm is from Frankfurt and Witchburg
Look
University.
at that.
Maria Felicia
Beautiful.
is from the University of Napoli and the
Look at all that
Italian
resolved radio emission.
Facility. José Luis Gomez is from the Instituto de Astrofísica de Andalucía in Granada. Thomas Kriegbaum is from the
Sorry if I'm
FBI
not talking,
Bonn.
I'm just going to be posting this on social media. I'm just so hype.
What we have seen and what it all means. Sarah Issaoun is from Harvard and Smithsonian and Radboud University.
Thank you, Hub. Ooh.
Getting chills, man.
This is the first image of the supermassive black hole at the heart of our Milky Way galaxy, Sagittarius A star. For decades, we have known about a compact object that is at the heart of our galaxy that is 4 million times more massive than our sun. Today, right this moment, we have direct evidence that this object is a black hole.
Look at that thing.
The black hole
The warping
resides
of
inside
light.
the dark region at the center of this image, where its gravitational pull is so strong the light cannot escape, and only darkness remains. We call this region the shadow of the black hole.
Yep.
This region is surrounded by
Got a
very hot
shadow.
gas swirling around the black hole. This gas emits radio waves we observe with the Event Horizon Telescope. These radio waves create the glow we observe around the shadow of the black hole. From our image, we measure the size of the shadow of Sagittarius A star to be 52 micro-arcseconds on the sky.
52 micro arc seconds.
This is about
Wow.
the size of a donut on the surface of the moon as seen from Earth.
Jeez.
In reality, Sagittarius A star is about as big as the orbit of Mercury around the sun, but at a distance of 27,000 light years. Because the size of a black hole shadow is proportional to its mass, our image tells us that the mass of Sagittarius A star is 4 million times greater than that of our sun. It is really incredible that this prediction from Einstein's theory of general relativity matches the mass measured by the Nobel Prize-winning studies of stellar orbits in our galactic center. Today's image might look familiar to some of you. We were all amazed that the image of Sagittarius A star looked
Yeah.
so similar to that of the famous black hole in the M87 galaxy,
Indeed.
an image our team reviewed.
The black hole is
back
like
in
1,000
2019.
times lighter, though, in the
However,
than the M87.
Sagittarius A star is over 1,000 times less massive.
Oh, did I just say
than the
that?
M87 star.
I didn't predict that.
Sagittarius A star were the size of this donut right here,
Hey,
tiny.
very tiny donut.
M87 star would be the size of the Allianz Arena, the Munich football stadium, just a few kilometers from where
Imagine
we are
you could have a
today.
donut that big.
On top of that, Sagittarius A star consumes gas at a much slower rate than M87 star. And these two black holes also reside in completely different environments. Sagittarius A star resides at the center of our small spiral galaxy,
Yep.
whereas M87 star
a big
resides
elliptical.
at the center of a giant elliptical galaxy and ejects a powerful jet of plasma. Despite all these differences, the images of these two black holes look very similar. Why is that? This similarity reveals to us a key aspect of black holes. No matter their size or the environment they live in, once you arrive at the edge of a black hole, gravity takes over.
The Event Horizon.
The journey to the edge of Sagittarius A star spanned decades of technical and scientific developments, and I will pass it on to my colleague Thomas to tell you all about our adventure. Thank you very much.
Yeah. Looks like the shadow is like more elongated in that image as opposed to M87's.
Thank you, Sarah.
But
Imaging a distant black hole would not have been possible without a big telescope of very high magnifying power, or angular resolution as we astronomers call it. To achieve this, astronomers combine radio telescopes located around the globe to create a super telescope which has
yeah,
the
very
size
long
of the Earth.
baseline interferometry. Look at
This
that thing.
technique is called very long baseline
Oh!
interferometry,
Predicted it again?
VLBI.
I'm just
While
a
the Earth is
psychic here.
rotating, all telescopes
6
observe
a.m.
the same astronomical objects for several hours. At each telescope, the data are recorded on hard disks and are accurately time-tagged by precise atomic clocks. After observations, the data are shipped to processing centers where they are combined in supercomputers.
Yeah, you need those computers to do that.
Supercomputers are called correlators. After a number of
I can't
quite
imagine the
complex
work that
data
goes into all
analysis
that.
steps,
Like
result
connecting all that
in
data.
high-resolution image of the radio source. It took more than 25 years to optimize this observing technique and make it work also in the short wavelengths 1 millimeter band, where the angular resolution is highest. It required the development of quite complex and very technically challenging
New screensaver?
techniques and data acquisitions
Is that going to be
So that
replacing this
the
on my phone
wider
screen?
observing bandwidth,
Potentially. Very potentially it might.
could be used to achieve this better sensitivity. This sensitivity is really needed for the accurate imaging of the faint event horizon scale structures which we are now seeing in Sagittarius A star. A decade of pilot studies paved the way in Europe and in the US for the formation of the Event Horizon Telescope. The EHT is a VLBI network of telescopes which combines radio waves at 1.3 millimeter wavelengths. This wavelength is short enough to see the swirling matter around the black hole.
That's like the wavelength I used in my research.
During the Sagittarius observations in 2017, the EHT combined 8 telescopes. Since then, the network has
Alma,
already
shout out
grown to
Alma, let's
11
go.
millimeters.
And I've been to the SMA
Radio
in person,
telescopes of
so
the EHT are located at
those are the
public
two
level high sites
that I
to minimize
rep,
the
if you know what I
influence
mean.
of the
But
atmosphere and the water
look at that
vapor
range we got,
conditions.
though.
Examples are the ALMA and APEX telescopes.
Imagine if we had,
the
like,
Atacama Desert in
one in
Chile,
space,
the IRAM 30-meter telescope in the
and then we
Sierra
get bigger
Nevada,
than
close to Granada,
Earth
Spain,
diameter size
and
telescope.
the NUEMA interferometer in the French Alps. With this, the EHT achieves an angular resolution which is sufficient for the imaging of such distant black holes, and also sufficient for the matter surrounding these black holes. To give you an idea, the EHT can see 3 million times sharper than the human eye. So when you are sitting in a
Pretty
Munich
sharp.
beer garden, for example, one could see the bubbles in a glass of beer in New York. Sagittarius A star was observed by the EHT.
Oh, hey there, Jazz. Thanks for coming by in the chat. This is definitely one of the coolest images of the century. I mean, look at that. Look at it.
Also included,
Isn't it
for
beautiful?
example, special places like the South Pole.
Ah,
The telescopes recorded a total of 6,000 terabyte of data.
6,000
which were then shipped
terabytes.
to the 2 correlator centers, one being in Max Planck Institute for Radio Astronomy.
6,000 terabytes? Isn't that
and
like
the other one at
6
MIT
petabytes?
Haystack
Is that
in
correct?
Massachusetts,
Can someone check me on that? I don't know what 6,000
in the
terabytes
US.
is. I should be able to
The
convert
amount
that.
of processed data is really very, very huge.
Oh, it's
It would
0.006
basically, if you would print
petabytes.
this data on A4
No,
paper
6,000,
stack,
right.
paper stack would
Yeah,
reach
6
1
petabytes. I got it right.
Of course, we are not going to waste such much paper. After correlation, the calibration and sophisticated data analysis took several years and required the development of many, many new tools.
You tell
by the
me
members of the EHT
you couldn't just
Corporation.
crack open this book,
This
the so-called,
development,
like,
we
Bible of
also honor the
interferometry
substantial contribution
and do
of
it?
very many
No,
young
probably not.
scientists who just start their careers now. For the details of this amazing imaging process, I would like to refer to my colleague and the next speaker, José Luis.
Thank you, Thomas. Thank you very much. Yes, as my colleague Thomas mentioned, the EHT is like a giant Earth-sized telescope, but it doesn't work like a regular telescope.
No, because they're not all
Instead,
connected.
the radio telescopes of the EHT work in pairs, with each pair
The
collecting
baseline.
the information required to obtain
Talk about
an image.
baselines.
As the Earth rotates, the separation and orientation between telescopes changes, providing this extra data that we need. With the
The
8
Earth
ring
rotation
telescopes
synthesis
of
right
the
here.
EHT, we have enough information to obtain an image, making the EHT the only existing instrument humanity has to image supermassive black holes. Imaging Sagittarius was, however, significantly more challenging than M87. Oh my God. It was really
Yeah, it took 3 years in between the pictures,
Our
but
line of sight to the galactic center is obscured by matter,
yeah,
which
dust.
scatters radio waves coming from the region around the black hole. But most importantly, as shown in these computer animations,
Ooh, look
the
at
gas
that.
in these 2 black holes moves at the same speed, nearly as fast as the speed of light. But Sagittarius star is over 1,000 times smaller than M87. This means that the time that the gas takes to orbit Sagittarius is only just a few minutes, while it takes days to weeks to orbit the larger M87. This
Right.
means that
It's kind of
the gas
counterintuitive, I think.
around Sagittarius
Small black hole
was
has a
actually
shorter
changing
orbit
while we
time.
were observing it, it was like trying to take a clear picture of a running child at night. So you would imagine how difficult
A running child at
racing
night
drove us for many years.
with no flash.
So we EHT scientists has developed sophisticated new tools to account for this rapid movement of gas around Sagittarius star. Tens of millions of images of synthetic data created to best resemble that of Sagittarius star have been produced in supercomputers around the world to refine all algorithms, like searching for the best lens and filter to get the sharpest ever image in your camera. The EHT collaboration has produced thousands of images of Sagittarius star using classical methods, and EHT tailored new algorithms for imaging interferometric data. As shown in these images, each one of these images is
Look at all those
slightly different.
simulations.
But by averaging these images together, we are able to emphasize the common features, finally revealing the giant larkin.
Yeah, because typically in the
first
process of making these
But it
images,
is
there's
important
actually
to note that
a
not all
ton of
images
different
look
solutions
alike.
that could correspond to
We
the
found
observed
that
data, I
we
believe.
can cluster these images into 4 different categories. The vast majority of them are contained in 3 clusters with only ring images that only has some changes in the brightness distribution around the ring, and only just a minor cluster with images that doesn't look quite like ring images. Through literally years of exhaustive tests, we are now confident to have captured the first image of the black hole in our galactic center. Sagittarius star now holds the record previously set by M87 of the most thoroughly vetted interferometric image that has ever been made.
Out of 2 possible candidates. Just kidding. No, it's a lot of work.
Of the images, as well as exhaustive modeling of the interferometric data, has revealed that all share exactly the same ring size, precisely measured to be 52 microarseconds, in perfect agreement with the size predicted by prior observations and theory. Of course, we are thrilled today to show the first image of the black hole in our galactic center. This,
Yeah, imagine
together
linking
with the
satellite
personal release
telescopes.
of an
Agreed.
M87 image,
Like,
fulfills
an
the
increase in
initial
resolution
visionary
getting down to
goal
like
of the EHT.
sub-micro
But
arc
this
second
actually
level.
only marks the beginning of an amazing area in the study of black holes.
But how would you like link it up?
The ongoing
Oh,
expansion of the
atomic
EHT
clocks.
and the significant technological upgrades will allow scientists of the EHT to release even more amazing images and, of course, movies of black holes in the future.
Movies?
And now, to learn what
As
this
in,
image
like,
tell us about
moving
the black hole
pictures?
itself, I pass it on to my colleague Christian. Thank you.
Dude, imagine like getting like movies of gas swirling around a black hole. Oh man, that's gonna be sick.
Thank you, Jose. To interpret the image and to learn more about black holes, we performed detailed models how the gas and the light behaves in the direct vicinity of black holes. Our models have 4 ingredients: the black hole, magnetic fields, gas circulating the black hole, and the light emitted by the gas, which is finally collected by the telescopes of the EHT. Astrophysical black holes can be fully described by their mass
Their
and
spin.
their rotation.
Yeah.
Black holes can spin either
And technically
in
they're
direction
charged, but
as
we don't
the
talk
gas
about that.
or in the
We
opposite
don't talk
direction.
about
For the models
charge.
or for the image and the source in the galactic center, we know the mass estimate very good from stars orbiting it.
Thanks,
However,
Andrea
the
Ghez.
spin of the black
and
hole
Reinhard
in the
Genzel.
galactic center is rather unknown. In our models, we let mass and matter fall towards the black hole, and this matter forms a disk around it.
Ooh.
The gas in the disk is circulating the black hole. And
Oh
heating up.
wow.
While the gas is heating up, it starts glowing.
Look at those
So
jets.
thus, in the EHT image, we see the glow of the infalling and outfalling material. Similar to the black hole spin, We don't know exactly what is the orientation of the black hole towards the Earth. And changes in the orientation lead to different image structure and different positions of the bright spot around the ring. Therefore, our modeling needs to cover a large range of possible spins and inclinations. Therefore, we built the largest and most detailed image library for black holes ever.
Oh my,
For
look
this
at that.
purpose,
Look at all
we
those
use
images.
supercomputers around the globe, spending billions of CPU hours creating petabytes of data.
6, I
Finally,
thought, to be
we have
precise.
obtained millions of black hole images, and we compared them not only to
Or maybe that's
previous
just from the
data, but also
from the
to
measurements,
historical
not
and
the simulations.
complementary data. Our best bet model, which is playing now, shows a lot of fine details. You can see these fine arcs going around the black hole. However, when we consider the resolution of the Event Horizon Telescope, as my colleagues explained, these fine features are blurred out. And you will see this soon. This will switch on to the blurred image. So now you see the transition to the blurring.
Yep. The limitations of the resolution.
This is the resolution of the Event Horizon Telescope. What we found is that the black hole in the galactic center is rotating,
Look at
and it's
that.
seen face on. The
It's face on.
implications of our modeling with
Wow.
respect to theory of gravities will be explained by my colleague Maria Felicia.
So it's got an inclination of 0, huh? Or must be around that.
Thank you, Christian. As our nearest supermassive black hole, Sagittarius star can be studied in ways that are not possible for other sources, making it a unique laboratory for exploring the astrophysics of black hole
Oh.
and testing prediction of Einstein general relativity.
Oh yeah, that's gonna be sick.
We relaxed the assumption
How many predictions we're gonna get?
that Sagittarius star supermassive black
confirmed
hole
from
is
this?
described by Einstein theory and quantify possible deviation. Our finding from this new measurement of Sagittarius star provide further evidence that astrophysical supermassive black hole, independent of their mass, are described by solution of Einstein theory. For Sagittarius star, as we found for M87, the inferred size of the black hole shadow is consistent with the prediction of general relativity within the 10%.
10%,
This
wow.
consistency is in spite of the fact that Sagittarius star and M87 are feeding on matter at dramatically different rates, with Sagittarius star accreting 1 million times less matter. So
1
our
million times less
conclusion
matter.
indicate that Einstein theory
So it's
is
proportional to
still
the square of the
holding
mass then?
strong. And in addition
Which I think is
of what
right.
was observed for M87, now we have the most compelling evidence to date that the supermassive compact object at the center of our galaxy is a black hole, and that it is in all likelihood described by Einstein theory. We know
Smoking gun.
black hole, and in particular, the vicinity of
Because
the
technically
event
everything else
horizon
before it was kind of very
are
strong
becoming an
circumstantial.
observational
If we're going to be
test
like
bed for
letter of the
gravitational
law about it.
physics.
But this is just like,
This
yeah,
environment
this is just
offer us the unique opportunity to determine
full-on confirmation
where
here.
and how Einstein theory break down. And if it does, of course, will transform our understanding of gravity and the property of space and time. We know very well that the idea of testing Einstein theory using our galactic center black hole is not new. But the result we have shared today represent an important step forward. So I'm delighted to be able to say that we have finally imaged the supermassive black hole at the heart of our galaxy. These measurements have opened a new window onto studying black hole and their role, their central role in our universe. The years ahead, of course, will transform our understanding of black hole and the fundamental nature of gravity.
Oh man.
So stay tuned because the best is yet
So
to
exciting.
come. Now, I will hand over to my colleague Anton, who will give the closing remark. Thank you.
Sorry, I'm just posting all this stuff on social media, just sort of like shouting it to the world. Look at the black hole! Look at it!
This is it. This is a big, no, it is a huge moment for everyone in the Event Horizon Telescope collaboration. It's the next level.
Leveling up.
And I'm proud
Let's go.
of everyone in our entire worldwide team. They have worked so hard for this latest breakthrough. You are the first to see our image of the black hole in the center of our galaxy, as close as it gets. Imagine this. We have combined the world's greatest radio telescopes into one Earth-sized camera. To be honest,
It's teamwork.
after doing this for 40 years, I'm still astonished each time we pull this off. Let's shine a spotlight on the European facilities within the EHT.
Shout out.
Begin with the ALMA Observatory.
Yeah, let's go, Alma!
ALMA large millimeter array.
That's the telescope I
5,000
use
meters
for my
altitude,
research.
Chilean desert.
Right
This
there.
was our game changer. Its sensitivity, because of its huge collecting area,
Unprecedented.
was the difference in measuring
Oh, there's Iran.
distant signals. And the 30-meter antenna in Spain of IRAM, this has been our flagship for over 2 decades. It is essential for making the sharpest image.
I'd like to visit it one day.
The APEX, the Atacama Pathfinder experiment in Chile, near Alma.
I'd like to visit
is
all
a
of these
valuable,
telescopes. All of them.
precise
Been to the
and
SMA.
accurate
That's the only one from
our
this group I've
signals.
seen.
And the NOEMA, the Northern Extended Millimeter Array in the French Alps, with this huge collecting area and super sensitive receivers, has given a further boost to the EHT.
I mean, look how big they are compared to people on the ground.
And a supercomputer, our correlator,
Oh,
is a
look at
hub
that
for the
correlator.
processing
Look at
of
all that
enormous data sets
data it has to go
required
through.
then extract our images. These
How do you wanna think about the
facilities, which
cost?
include the 3 largest antennas within the EHT, and the support from our funders, yes, that's us, the taxpayers, are a sustainable foundation for the continued success of the EHT. And we acknowledge the support of the national funding agencies, of the European Research Council, and of the Commission. Now that said, in its DNA and by our design, the EHT is a truly global enterprise. Well over
Oh.
300 scientists from over 20 countries. And add to
Teamwork
that telescope
right here.
designers, builders, engineers, technicians, and staff. Their contributions are what the
Some people are
scientific
black holes
community
themselves?
focuses on.
I'm just kidding.
In 2019,
Some really pretty
little
black hole
over a
pictures in
century
here.
after Albert Einstein revealed his theory of relativity, and after decades of pioneering preparatory work, we presented the first image of a supermassive black hole in the center of the galaxy M87.
This one.
Nobel Prize-winning measurements
What do you know?
by Andrea Ghez and Reinhard Genzel. And we're so happy, Reinhard, that you're with us.
Oh, hey there.
With
Good
their
morning.
teams, they showed that there must be such a black
Thanks
hole
for joining
in our
us this
galaxy.
morning.
And we made this black hole visible for the first time. And it confirms their conclusions. So what about Einstein? Would he
He was
smile
right.
seeing all this, hundreds of scientists still not having proven him wrong? I rather think that he would be ecstatic, seeing all the experimental possibilities we have in this field today.
Yeah, honestly, imagine we could bring him today.
So,
I would be like shook.
mission
I'd just be like,
accomplished.
what?
Yes, but there's so much more to do. We now want to go on and make movies. We want to study magnetic fields.
It's been
We wanna
over
look at
100
the
years
jets in
since they came up
galaxies.
with
And
general
yes, we want to
relativity.
tackle gravitation theory again. New antennas in the EHT, like NOEMA and the African Millimeter Telescope, and ever-improving technology will enable us to do that and much more. So today we're celebrating the first image of the supermassive black hole in our galaxy. And we're talking about what it tells us and why that matters. And tomorrow we'll be back at work unraveling the mysteries of black holes in the universe. Thank you all for being with us today, and now over to your questions.
All right, now we get to hear some questions. Let's see, what are people thinking? I think the big questions are probably going to be like, why is it really bright? Like, it's much brighter around those certain edges than like M87s.
Thank you to our speakers for sharing this remarkable result with us. Before I open the floor for questions from journalists, I'd like to remind everyone that we have extensive press material, including images and videos, on ESO.org.
If you want to check out
For
those
those of
links.
you watching online, please stay tuned, because at 4:30 we have a Q&A panel where members of the public will be able to ask questions
Ooh,
to
the public.
EHT experts.
Nice.
But on to questions from the media. If you are a journalist here in the room, please raise your hand. Take your mask when asking a question and speak very closely to the microphone, otherwise we cannot hear you properly on the stream. Do identify yourself, whom you are reporting for. and
Identify yourself.
And then we will answer questions from members of the media watching remotely who have sent in plenty of questions already a little later. So do we have any questions in the room from journalists or media?
All the hands go up right now. I'd be like, any question? Come on.
Right?
D-
If
not-
not,
not all
we
of
can
them.
start. Oh, okay.
I was about to say, come on.
Hi.
Really?
So I'm Teresa Paneke. I'm actually a PhD student here at ESO, and I do science communication online through social media. So thank you very much for this amazing result. I would like to ask, because we've talked a lot, or it's been said a lot, that M87 has an active black hole, whereas our black hole is maybe not accreting as much material. So when we just look at the image, they seem to be equally bright. Of course, there's the distance difference, but
That's true.
what exactly is the material we're seeing there? Do we have an idea about accretion rates? So what is the difference between M87 and Sag A in that regard?
So as you already hear, the difference is the central mass already. So the galactic center has roughly a mass of
1,000
4
times.
million solar masses.
It's a factor of 1,000 between the
Professor
two.
Gensel showed us already. And M87 has billions of solar
And
masses.
Andrea Ghez, don't leave her out of the equation.
The other difference that you may have noticed on my animations or from images of M87 is a powerful jet that is generated in M87. For the galactic center, we see it, as I showed you, phase on. So the jet,
That's right.
if it's existing, is pointing
What
towards
is
us. It's
M87's
very tiny,
inclination?
so we can't, at the moment, image it, and I would refer then to my colleagues to explain you a bit what we need to finally detect it. And I think these are the three major differences. It's the mass, it's the jet that's existing, and as already you said, it's a different mass accretion rate, which we have for both systems. So maybe one of my colleagues.
Christian, yes.
Imagine being in that room.
To obtain the image, we need to have measurements.
Be so
of,
sick if you're like in the room there,
with
you see the picture
antennas
come up on
at
screen.
different separations to measure features that are very small and features that are very large. So in order to capture a possible jet in Sagittarius star, and to actually capture the jet that we do know exists in M87, we need to have measurements of telescopes with short separation to see these larger scales.
Yeah.
We lacked that information.
Don't
during
have the small scale
2017
structure.
observations.
That's right.
And this is why we did not see the jet in the M87, and we have not seen any jet inside JSR. We do have new antennas in the observations that followed the 2017 campaign, and we do expect to see the jet in M87. It is still unclear how bright, if there is a jet inside JStar, but we will be chasing it, of course.
What can you do then if it's the small scale structure you're trying to get, or the small scale separation between the telescopes? Because
my name is Camila. I am with the Brazilian podcast Astronomia em Meia Hora, and I wanted to ask if the collaboration has other targets in mind already. Anything
pick the ones that I'm measuring,
to observe.
and then confirm my black hole mass, please. It's probably a long shot.
Thanks for the question. Yes, of course, we have other targets in mind. I mean, during this observing
Can you do NGC
runs,
3258?
not only
That's a published
observed,
result from the group I'm in.
Sagittarius A star, but we observed also
It's like the
a
most
number of
precisely
AGN,
measured
some of which are
from
very
ALMA.
close by. And data analysis of this is still ongoing, but give you a warning. Since they are so distant, we will be not so able to see these beautiful shadow-like images immediately. So it would require more sensitivity to really look at the very closest objects, and we are at the moment surveying the sky to find these.
Thank you. I'll take questions online now because the list is piling up. So this one is from Hans Heckenberg from New Scientist Dutch edition, and it's addressed to Sarah. What open questions that we currently have about the structure of black holes can be answered by this image and follow-up images of Sagittarius star?
Ooh, that's a loaded question. Yes, so open questions that we can answer. I think Kristen's portion of the presentation summarized really well the major things we found out about Sagittarius star, which is one of the unknowns is the black hole spinning, which we have the answer to that. Yes, it is. And
Spinning
what is the
hole.
orientation of the black hole with respect to us, which we also did not know before.
It's
And now
a Kerr
we're
black hole,
fairly
then.
confident that it is pointed more or less towards us.
Which
based
technically
on,
we believe all black
so,
holes at the center of the
these
galaxy are Kerr black holes, but
properties, this
confirmation
knowledge
of that
the,
is
fundamental
difficult.
properties of the black hole will help us study the astrophysics of the black hole in more detail later on, and also how we interpret the images. The spin and inclination have very important roles in how the image looks and how we interpret the astrophysics we can learn from it. Future observations of Sagittarius star, of course, our current observations from 2017 also have polarization information.
To crack out this
which,
book now.
We are planning to
Learn about
start
more
working on
black hole
like Anton
stuff.
said, tomorrow. That will tell us information about magnetic fields around the black hole, and magnetic fields can tell us about how the black hole eats gas and ejects possibly a jet or outflow. So as Christian said, we still don't know if Sagittarius star has a jet.
See
Some
that
of the models
synchrotron
seem to
radiation
hinge
then,
towards that direction,
that close
but
to the black
magnetic
hole.
fields, learning their configuration, how they look around the ring of Sagittarius star, will help us answer these questions very soon.
Thank you. Okay, I'll continue with the online questions. So we have from David Castelvecchi reporting for Nature. This is addressed to any of you. How does the measured angular size compare with the mass of 4.15 million solar masses measured by Genzel's group?
So how consistent is that size? Yeah, with the measurement mass.
Was very important to have their measurement, their astrometric measurement to us, because what we found that the size of our ring of the shadow is consistent with that mass. As Sarah said before, that the size is proportional to the mass and to the distance. For us was important this, and
thank you.
I think they said it was like within 10%,
online questions.
which
So
by astrophysical
from
standards,
Sanja
that's
Van
very
Kerk
impressive.
Reporting for Wolfgang magazine in Vienna, also addressed to any of you. What are the difficulties when observing and analyzing Sagittarius A star? Maybe more for
The
Jose.
dust, or like a lot of
Very happy to
the stuff,
answer this.
the stuff in the
many.
center.
Oh my God, where do I start? I mean, the most difficult part of SciJ is that it's a very small black hole as compared with M87, 1,000 times smaller than this. And then we had to try to find a way in which we can overcome these extreme changes in the emission that we were observing, as we were explaining before. In order to capture an image of the black hole, we need to take a very long exposure snapshot. We are observing these sources for 8 to 10 hours.
At a time.
The
Whoa.
basic principle of the
And all that
technique
data
we are
from all
using
those
is that
telescopes.
during those 10 to 8 hours, your object is not changing. And this is exactly what refuses to do Sagittarius star. So in order to that, we have created these new tools that allow us to get a little bit blurry image, adding a little bit of extra noise to compensate this variability, so that even though the image may be a little bit blurred than the image that we got
It's pretty
from,
insane that we can
from
actually
M87, we do capture
see
the,
that
the,
sort of
the main features, the
that,
most salient nature
short time scale
of the black hole.
variation.
And this is the ring structure, and all these images that we were showing before, they all share the same ring size. What we were not able to capture is what is, the brightest emission around the ring. And this is because it's changing. So we are getting these different images, all consistent with a ring, 52 microseconds, but the emission around the ring changes when we make slight changes in the way we make the images, like we change a little bit the lens or we change a little bit the filter, and then the image looks a little bit different. But the main image is there. And all this analysis is what took us more than 2 years, from 300 people in the collaboration, from doing the imaging, from doing the analysis, etc.
I can't imagine having to sort through all that data. I mean, it's good that you have like 300 people.
So I'll continue with the online questions. We have one from Filip Ogorzelski from TVP Nauka. This is addressed to any of you again. How much matter
That dude at the
is
bottom
being
right
absorbed by the black
is like
hole
on the
in
HT
center of the
website.
Milky
I don't know what
Way?
he's doing. Watch up like Twitter or something comes on or something. I don't know.
I'm not exactly sure what he means by absorbed, but the accretion rate. Yeah. So actually, these black holes in the galactic center is secreting very, very less matter. They are basically, this black hole is basically starving. The accretion rate is
Yeah, we don't
extremely
we don't have an active
and
black hole.
Yeah, the accretion
Which
rate
is-
is extremely low. Maybe Sarah.
Which is kind of surprising considering how bright
Sorry
the
for
image
that.
is.
We
But
we calculated this for a fun EHT Twitter poll that we had. So if you were to have the same diet as Sagittarius A star scaled to your mass, you would eat 1 grain of rice every million years.
1 grain of rice every million years.
We have
Yo,
a
that kind of
question
hurts
from
me to hear.
Antonio Pires, reporting for astronomia.com. How much did the telescopes that recently joined the HT collaboration improve the
Imagine that's
results
your
from
like
the previous
diet
observations
for a
in
million
terms of
years if you could live to be a
resolution
million
and
years.
sensitivity? Will we be able to increase the apparent aperture
Imagine
by
that
using
you could
space
starve for that
telescopes in
long.
the foreseeable future? Speak perhaps for Thomas.
Well, first, of course, this image which we created now has the same configuration. So the 2017 data of M87 and Sagittarius A star based on the same telescope configuration. In 2018 and following observations, we have added more telescopes. Now we have 11 telescopes, so we fill the UV plane much better. That means we can much better make a synthetic telescope, and the participation of NOEMA and also of Kitt Peak, for example, provided additional baseline sensitivity. We also expanded the recording rates and doubled the observing bandwidths. So all this lets us hope that in 2022, where we just observed the source again a couple of weeks ago, we will get a much better image.
Thank you.
Even better.
Okay, we have one from Dave Adalian, reporting for earthsky.org. And I think Christian would probably be able to answer that one. When the orientation of Sagittarius A star is said to be face on, does that mean one of the black hole poles is directed towards Earth? Do we know how fast Sagittarius A star processes, and what is the nature of the particles ejected?
In principle, the inclination of the orbit of the
Okay,
stuff around it
so
is face on.
Let me start first. So we found that it's face on. So this is correct, that
The black
one
hole,
of the
yeah.
spin axes is pointing more or less towards us. The other part was about the material or the emission actually that we see. And what we model is synchrotron radiation. So you have
Woo!
particles,
Relativistic
mainly
cyclotron radiation.
gyrating magnetic fields, and while they gyrate the magnetic fields, they emit emission, and this emission is synchrotron. And this is what we actually see.
E cross
And there
B.
was a
Let's
third
go.
part. Could you please repeat this?
So it was the processes.
Yes. So precession, I think what you mean is spin. So what we have actually is we have some kind of best bet models. So we have not found an exact model which could explain everything. So we have best bet models and best bet regions. And there we could say that it's spinning.
Right.
And it's spinning in a
Yeah,
same
'cause, like, you
direction
have-
as the gas orbiting it.
You
and
have
the precise number
interferometric
of the spin
data. When you
has to
convert it
be
into an
obtained
image,
in
there's a lot
upcoming
of possible image solutions that correspond to the measured data. So you kind of have to take sort of a best bet or a average solution amongst a ton of different possible
in
solutions.
Brazil. EHT observatories capture radio waves, but how do black holes emit these waves, and how can we build an image?
It's more of
with
the
it?
gas,
Who
right?
wants to take this?
Or the stuff around it, right, that's emitting it.
emission, how it produced is I already explained. That's the synchrotron radiation. So basically you accrete gas which is electrons, they gyrate, produce the emission.
Right, so I think people are
for
confusing
the
that the black
details
hole is not the
how we
emitter
actually detect this
of the
and so
stuff.
on,
It's
I would refer to one of my colleagues
causing
working
the
on data
accreting
processing
material on
on
it to radiate significantly.
Jose, Thomas?
Because nothing can come out of the black hole.
Then
Right?
the most important part, of course, is to get an image. As we were explaining before, the HT doesn't work like a regular telescope, so we cannot build a telescope the size of the Earth, obviously. We cannot do this. But what
But imagine
we do
if you
is
could.
we have these different
No, you can't.
telescopes that act
But if you could,
like segments of
that'd be
this
pretty sick.
huge telescope. And then we collect the signal from all of them, and
Or like as big as the solar
create
system.
synthesize the virtual telescope on a computer. Once we do this, and then it is possible to have basically like the Earth-size telescope and
Hey
get
there.
an image.
Good morning,
like you
Cody.
get an image.
Thanks for joining us.
With your mobile phone, but it is significantly more complex. You have to do. You have to make the images on supercomputers, so it's a process which is extremely complicated. But at the end, you are able to finally obtain the images of these supermassive black holes.
Okay, thank you. Another question online is from Doris Urrutia, reporting for Inverse. How did you feel when you saw this new result? What was the big reason that you felt excited enough with your finding to share it with the world?
I'd just be like,
Sarah?
Yeah, so I did my PhD research on Sagittarius A star, trying to chase down this jet that is maybe real, maybe a myth.
elusive,
So,
to put it
I
simply.
was working on images of Sagittarius star.
If it's
at a
not
lower
accreting that much
frequency
material,
than
could it
EHT,
be emitting
so
a jet?
images that aren't quite at high enough frequency to be able to peer through all the gas and see the shadow. And I was trying to understand where this radio emission comes from near Sagittarius star, try to see if we could constrain the inclination of the black hole from my observations. And until today, I was also the record holder for the best image of Sagittarius star. So when working on EHT, I saw the image of the shadow. It was a really special moment because I've been working on this source for a long time through my PhD and trying to understand its properties. And there it was, staring back at me, and I felt, shivers and excitement. And it was revealed as part of the whole imaging teams coming together.
Downside of studying extragalactic black holes like myself.
I was in Japan with a few people
Unless
at a
EHT looks at one of my
Galactic Center
targets.
conference, which was quite funny. It was midnight Japan time when we had the telecon, and we all huddled together, and the images, like Jose was leading the telecon, images were revealed from all the different teams, and everybody saw this ring of the same size. And it was such an exciting day and very memorable to finally see this object I've been working on for a long time.
How? Did you want to add?
I wanted to say one thing to Sarah. She's still the record holder.
Yeah, but now I have to share it.
Well, I would share it as long as, like,
correct, but
I don't know,
as a little bit older person,
to have a picture like
I
that in the
realized how it
world,
all started,
it's worth
and I
sharing.
think it took now more than 30 years to get the image. So we had this idea long ago, and at that time, when we started observing, the first experiments at 1 millimeter failed horribly. And we have to step back to 2 millimeter before we could do it at 1 millimeter again. And I saw that over the years,
30 years, imagine.
improved so much that
I haven't been
really
alive for that
very,
long.
very good feeling.
Have you
to
got your
see now that
PhD
it
yet,
has
says Cody
worked
Loads?
and
No, I
that
have
we
not.
find
Give me
it
about
so
a year.
Great.
A little bit more than a year.
Gratitude
June
for
2023 is my expected graduation date.
Okay, one more question online. It comes from Diego Garcia, reporting for Canal Sur TV. This is addressed to Jose because he wants you to answer in Spanish, but someone else could answer in English as well, I suppose. During this process, what have you discovered at a scientific level about Sagittarius A star that was not known before? And then there's a second part to that question. What are the biggest differences between this image and the one of the black hole in M87?
Okay, thank you very much, Diego. I probably should answer this in English for the whole community. Thanks again for your question. Yes, I think the most important thing we have learned is that first we have the visual confirmation of the black hole that was predicted a long time ago. As my colleague Christian mentioned and Maria Felicia, now we have a constraint about how fast this black hole rotates. And this is very important because we think that the rotation of the black holes provides the energy that powers this huge jet.
I wonder if you could like could you measure like the frame dragging then? Because you have like a rotating black hole, it's supposed to drag the space around it. We probably don't have the resolution for that, but
about the differences and
I don't know.
Yeah.
my colleagues moved the question already.
All right. Okay, it's fine.
If they can fetch it.
Sure. No, it's fine.
Okay.
Sorry, I forgot.
Also because we, for the second time, we were so close to the event horizon, and then we were able to test gravity at different regimes.
What is the event horizon radius of Sagittarius A star at 4 million? I mean, that's easily calculatable. That's GM over C squared.
Incredible.
And we know M is 4 times 10 to the
I have a
6.
question back, and it was 2 parts. What have you
Probably should
discovered about
calculate that.
Sagittarius A star that was known before, and the differences between the images between MET7
Yes.
and
Well, the images are surprisingly similar. I mean,
Thank you,
so
Cody.
as indeed
Appreciate
these
it.
two black holes they both live in completely different environments. Yet at the end, the image is just mainly made out of the gravitational pull, as Sarah was mentioning. So in that sense, this confirms one of the most important predictions from general relativity, which is that these are the most amazing, extravagant objects in the universe, yet the simplest. They are just.
You just need mass, spin, and maybe
as
charge.
Simple as a a sphere or a circle in images.
Thomas?
Well, also with regard to the published results from gravity, I think there's a major difference. M87 is far away and it's much bigger, so it varies much slower. But in Sagittarius A star, we really can see the variations. I mean, we see basically bright features moving around. Although we are not able really to trace their motion exactly, we have published in our papers some models which explain this motion already. And I think the next step would be to
Sagittarius
parameterize the
A star is
motion
like
so
30,000
that one
light
can
years
do
from
more
from
science on it.
Earth, and yet we can see that those variations. It's pretty sick.
Continue with the online questions. We have one from Alejandra Lopez reporting for El Tiempo in Colombia. This is to any of you. So she asks, but perhaps Christian, what is the orientation of the rotation of this black hole with respect to the plane of the galaxy? Do you have an answer to that?
Well, it's based onto Earth.
So what I mentioned is we see it face on, and according to our models and this bad region, the rotation is in the same direction as the gas. And please, all my colleagues, correct me. It's in a counterclockwise way when you look on it. When you look the images, it's turning counterclockwise. At least in the simulation. So the simulations, you see that it's turning in a counterclockwise way.
We have time for one more question.
One more.
If
What's it
I
going to
have
be?
Journalists here in the room. If not, I'll continue with the online questions. And we have one from Tushnet Physics World. Do you have any ideas on why there is such mass difference between Sagittarius A star and M87? They are both supermassive black holes.
Oh, that's a hugely unanswered question. We don't have an idea as to like how those formed. That goes into like galaxy formation and evolution.
So that's most likely to do with the evolution of the galaxies in which they are found. M87 is a very giant
Elliptically, and we're a spiral galaxy.
Merging many galaxies with many black holes together, while our galaxy has been going through much less evolution.
Okay, thank you. All right, I will stop now because we are almost at the hour, and I will thank our speakers again, and thank you all for the questions, also for those watching remotely. Journalists are now welcome to approach our panelists and other experts in the room. So EHT experts have a badge with an orange collar in it, and then there are also other experts who are not part of the EHT team but can answer questions about the research, who have a badge with a green collar. And we have interview areas available here and up there, and you can approach myself or one of my colleagues to be guided to them For members of the public watching remotely, do stay tuned because we have a YouTube Q&A coming up.
Ooh, YouTube Q&A.
And then before that, we'll actually have a special musical performance.
What?
Just before this
musical performance
Q&A session. Do go to @EZO on Twitter to find out more about it. Thank you all very much.
Wait, Arcade Fire is playing? That's awesome. Wow. Well, I didn't know Arcade Fire. I've actually been in the same venue as Arcade Fire about 10 years ago. Actually, 11 years ago at this point, when they were in San Francisco. Dang. That is actually really cool. I didn't know that.
Welcome everyone.
Oh, there's more to it, I guess.
European Southern Observatory in Munich, Germany. Very, very excited about this amazing image we just saw of our own black hole Sagittarius A star. And of course, as you already heard and know, this has been a worldwide collaboration. The Event Horizon Telescope is a collaboration of several telescopes around the world. And just like there are several telescopes around the world, we also have several black hole fans around the world from all different areas.
Right here.
Is why today, before we go into a very interesting Q&A conference through YouTube that you will be able to follow from your houses and from wherever you are, we have very, very special guests that want to share the love for black holes, for astronomy, and for music with all of us. It is my greatest pleasure and honor to introduce to everyone Win and Regine from the band Arcade Fire. It is amazing that you guys could join us all the way from the other side of the world. So hello, guys.
I don't know if this can be streamed on YouTube because I'm worried for like copyright reasons. I'm not entirely sure. So in that case, I think I'm going to be ending my stream then because I don't want to run into any sort of copyright issues. This whole stream, actually, I'm kind of concerned about copyright issues. But thank you guys so much for joining. It's been a pleasure to watch this with you so early in the morning. I will be ending my stream. I might do more live streams in the future. And until the next big black hole discovery, I will see you next time. Hope you have a great day wherever you are in the world.